Okay. The tablet has just updated, so let's see if it is going to explode. But we'll see. Here we are. Okay, we are done with thermochemistry, right? So, thank goodness. We don't have to worry about math for this chapter as much. Oh, really? Thank you, tablet. I didn't realize that. Okay. Cool. Okay, so I'll give you guys a second to trickle in. Okay. Cool. So if you thought this last one was hard, the last chapter, here we go. Oh no. This chapter is on quantum mechanics, which is, of course, the easiest part of chemistry. Yeah, I know. Yeah, don't worry. This one, it sounds bad, but the math is really quite simple for this class. If you end up being a chem major and you transfer and do a bachelor's in chemistry, you're going to take the real thing and you'll die. But that's okay. Yes, there's actually a pretty funny thing about statistical mechanics. Maybe I'll post it later. It's an interesting meme. It's actually a book introduction. It's like talking about how everyone who has studied quantum statistics has committed suicide. It's rather dark, but it's somewhat funny too. Okay, anyways, let's talk about quantum mechanics. So, first things first, let's talk about light. So, just so we remember, we're kind of out of thermochemistry for now. We're going to talk about it on Thursday. If you guys want to show up and talk about thermochemistry and solution chemistry, we'll be around for that. So, but anyways, let's talk about light. Light is electrog. No, let's not do that. Electromagnetic waves. So, we're going to be talking about light essentially here and how it interacts with atoms. Specifically, we're going to see that electrons can be excited by light. They can do things, and they can also release light back. And that's going to give us pretty colors, which gives us fireworks and all sorts of fun stuff. So anyways, light is an electromagnetic wave. It has an electronic field component, which goes up and down like this. And it has a magnetic field component, which is at a 90-degree angle. Essentially, that's going to be like in and out of the board or the tablet or your paper or whatever. We typically will just talk about one of those components. It really doesn't matter which one. And so both waves look like this. One of them is just tilted 90 degrees. And so waves are waves. So we have a few things to talk about. This. We have the difference, or how long it is between... since waves just go up and down forever, the distance between kind of the high points or the low points or the mid points, as long as it's, at the same spot in the wave, would be the same. And that's called the wave length, which is abbreviated with the Greek letter lambda. We also have another property, which is how high, that's really bad, the distance between the top and the bottom, which is called A, which is amplitude, which is related to the intensity of the light. So the bigger your amplitude, the more intense your light is. For sound, sound is also a wave, but it only has it's a pressure wave. It doesn't have the magnetic or electronic components. Amplitude is how loud your noise is. Amplitude is all about intensity. So how intense the light is, how intense the sound is, whatever your light thing that you're looking at is. Cool. And then the wavelength is another property we're going to talk about, which is the distance between the same point on your wave between oscillations. So typically that's either the highest point or the lowest point. They should be the same either way. Cool. We have another property, which is called... Oh god, that's really ugly. Which is the Greek letter nu. It looks like a V, but it's a fancy V. Which is the frequency. Which is how much time or how many oscillations per second. And that's basically saying how fast is it going up and down in a certain given amount of time, which is typically a second. Wavelength, by the way, it is done in meters or derivations thereof. And frequency is done in hertz. And 1 hertz is the same thing as 1 over a second. Of course, you're going to have, gigahertz, megahertz, terahertz, all sorts of abbreviations we can use with those. And we're going to see that wavelength again. While we can talk about them in meters, we're going to see nanometers, micrometers, all sorts of fun derivations of those. All right, it turns out that the frequency is related to the wavelength. Wait, is this frequency? No C, just C over lambda. Yeah. So C is the speed of light, meters per second. Lambda is meters, and so we're going to see that's how these guys are related. So C is 3.00 times 10 to the 8th meters per second. That's the speed of light. Speed of height. Yikes. Speed of light. And this is your wavelength here. And remember that's in meters. So meters per second divided by meters is 1 over second. Lo and behold, that's our unit of hertz. So again, this is frequency. So what this tells us is that something that is a short wavelength will give us a high frequency. So all these light waves travel at the same speed, the speed of light. And so if you can imagine, if the distance between the top part of your wave is shorter, you're going to be able to hit that point much more frequently by traveling at the speed of light in a given amount of time. You're going to just hit that top part much more often. And so we're going to see the opposite is true, of course. A long wavelength is going to be a low frequency. So just because if your wavelength is a meter long, compared to, 10 to the minus 10 meters, you're going to hit that top point much less often in that 1 second. All right, here's the other part. The energy of light, or what we call a photon, is going to be related to these two properties as well. And we're going to see that h is just a constant. This is called Planck's constant. It's going to be used all over the place in quantum mechanics. Of course, you don't need to memorize these constants, but it's one that we'll see a lot of in our homework. By the way, I'm going to post the homework this week for you guys, but it's going to be due next week because I don't want you to have to focus on this stuff for an exam that does not cover this stuff. So, yeah, just so you know. So I want you to focus on thermochemistry and looking over your solution stuff as well. Oh, I guess I have homework keys to do. Oops. Well, I'll get to those. Okay, anyways, so here we go. This tells us that a high frequency is high energy. What is that? That's this dude up here, the frequency, fancy nu. And really, I mean, nu is such a hard symbol to draw instead of looking like a V. Yeah, I know. It's annoying. But that's this part done here. So a high frequency, if your nu is high, that means you have high energy. And since we know that high frequency meant a short wavelength, that means that a short wavelength also is high energy. That's the information that we are going to get out of these particular bits of information. So let's go ahead and take a look at what we can do with this information. We're going to see that we have a whole spectrum of light. And let's say right here, just going to expand this. I'm going to draw you guys a rainbow. Green is next, yes. And yellow, orange, and red. Okay, there we go. So here, we'll just pretend that's how far this goes. This stuff is visible light. This is stuff that we can see, hence it is called visible light. This goes from roughly a wavelengths of 400 to 700 nanometers. So small little waves here. We're going to see that red light is going to be lower energy than purple light, for example. And we can tell this because the red light, which is going to be towards the 700 nanometer range, is going to have a longer wavelength than the purple light, which is about 400. So if you think about it, 400 nanometers versus 700 nanometers, this one is shorter, right? It's shorter length. And so as a result, it's going to have higher energy. All right, going on either side of those, we have two regions called infrared. And then here we have ultraviolet. So they are flanking red and violet, purple. So that's why those ones are going to be on either side. Infrared will have lower energy than red light, whereas ultraviolet will have higher energy than purple light. We're going to see that this is going to be short wavelengths towards this direction and long wavelengths on that direction. If we keep going shorter, we have X-rays and gamma rays going shorter. And if we go longer, we're going to have microwaves and radio waves. So presumably this is not something that you'll have, or that you should have seen before. Just understanding we have kind of classes of light waves that we can just describe, just saying visible light, it's going to be somewhere in that 400 to 700 nanometer range. So let's go ahead and do some math, because we love math. What is the energy in joules of a photon of 400 nanometers? Let's go ahead and look at what a purple light ray will be energetically wise. And let's also do it for the red one. And so we have our handy dandy formula. The energy of the photon is related to hc over lambda. So remember that h is that constant, and c, of course, speed of light. We can go ahead and figure this out. And so if lambda is 400 nanometers, let's go ahead and put some sig figs on those, because we like sig figs. If we want to get this into meters, we know our prefix is 10 to the minus 9, right? So that is 4 times 10 to the minus 7 meters. All right, math, here we go. So the energy, therefore, is going to be equal to 6.626 times 10 to the 34 joules times seconds times speed of light over our wavelength. And I've just put it into meters here because if we look at this, we want meters to be able to cancel out. And notice we have seconds to the minus 1 and seconds up top. Those are going to cancel out. So we should be left with joules. Oops. Let's see if Kevin has got the answer for us. I haven't seen him type anything today. He's probably ashamed after what happened yesterday. But we'll see. Okay. I'll do it myself, I guess. 6.626. Okay. Times 10 to the negative 34 times 3 times 10 to the 8 divided by 4 times 10 to the negative 7. Lo and behold, I did the math, and I've just lost it because I switched tabs. Doing all this fun stuff, we get 4.70 times 10 to the negative 19 joules. Okay. If we do the same thing but for the other one, math would be the same, but slightly different. So for the energy for the same thing over the 700 nanometer one is going to be, hold on, did I do this right? Oops. Is going to be 2.83, no, 84 rather. Oh my goodness. Times 10 to the negative 19 joules. So if we look at that, awesome, except your sig fig Star-Lord. Wait a second, how did you get a slightly different answer than me? Oh, whatever, it's close enough. Okay, but still sig figs. Give us 3. Okay, anyways, so looking at these two, we can see, again, that this one is higher energy. So this was the 400, this was the 700. We saw that the 400 one, again, has the lambda in the bottom. So if that one's smaller, our energy is going to be bigger. There's another, do I want to describe this yet? No, I don't. Okay. Any questions on this one? Easy math, right? Plug and chug. Formulas. Hooray. Yeah, go ahead, Tyler. Because they're in meters instead of nanometers. So that's where this it's right here. So it would be 4.00 times 10 to the second nanometers, but I have changed it from nanometers to meters. We have changed our units. So the conversion factor is 10 to the minus 9 for nano, right? Yeah. Okay. So Tyler's is on the 400 one. Where do we get the tons? Oh, where did we get this dude? Shame on all of you. We go back now to stuff you have completely forgotten. Let's go way back in history. I don't need this. Wow, look, it's going to be like the freaking first thing I've posted in this. Oh yeah, nano. Yeah, so don't forget your metric prefixes. Yes, so nano is there with the 10 to the minus 9. So it may not have been clear that I was talking about nanometers. So there may certainly be some of me on that, but yeah, don't forget these guys either. Okay, so there is where I got that 10 to the minus 9 from. It seems everybody has forgotten their metric prefixes. That's not okay, but it's kind of okay. That's alright. Okay, cool. I guess I'll write it in angry red. Alright, any other questions? Oh, why did I write 7 times 10? There, I'll fix that with a different color. Okay, cool. So, let's see, what else should we go to? Oh, yes. So, we're going to see that sometimes when light strikes matter, as in hits it, like a photon comes and hits the matter, an electron can be emitted. And so, we're going to see that here is a happy surface. Here comes our light ray. Ew, God, the yellow is awful. Okay, we'll write that in this color. We often just describe photons as h nu. Energy is what we're saying there. Remember, energy is... Don't forget that. We're going to see that... I'm going to say an electron can come out. And this is what's called the photoelectric effect. This is how, this is actually what Einstein won his Nobel Prize for. Not for relativity, but for photoelectric effect, go figure. So he was able to determine that when light comes in, it's going to kick out a photon. And it turns out the energy of the photon coming in is going to be equal to the energy of the electron coming out. We're going to see that this is going to be very specific in that only photons of specific E energy can eject electrons from a particular material. So if you tweak the energy of your photons, you may not get the photoelectric effect from the same material. And it turns out we're going to have a whole bunch of reasons why that's going to be, but for right now, just accept it. So this is also going to be kind of how solar panels work. So you have your light coming in, it hits your solar panel, it's going to spit out an electron. That electron is going to be, sent through, I don't know electricity or physics in that regard, but electrons moving is electricity, right? That's electric current. So you're going to end up getting your electricity that way. And so the conclusion from this was that that only certain energies are allowed, and the smallest amount of energy is called the photon, and it is quantized. And that means it has specific amount of energy. Alrighty, and so what the heck does this mean? Let's say here is Tyler, and he is walking up this slope. Or let's say he's like, actually, Tyler is going to be a snail. We're going to make him a snail. Oh, I guess I drew this shell all wrong, but whatever, here he is. I hope you like snails, Tyler. So Tyler is oozing up this slope. Yeah, I'm calling him slow. And instead, we have, who else do we have? Elizabeth will be our other one. So Elizabeth will be a normal person who is happy. And they're both going to go up essentially the same, idea, right? They're both traveling upwards. Up, one of them's going up a staircase, the other one is going up a slope. It turns out that Tyler here will have continuous energy. He's going up the slope. It's the same slope, just going up, oozing up. However, Elizabeth here is going to be going upstairs instead. And each of those stairs are going to be kind of this quantized idea. So each of those stairs, like as she goes up each stair, that's like an amount of potential energy she's getting, right? Remember gravity, the higher you are, the more likely you're to fall, right? Or not likely, but like the more energy you have technically if you were to fall off. So if Elizabeth were to fall off the end of the staircase here, she would have more energy if she's at the top. And so we're going to see that Tyler is going to get energy continuously as he oozes up the slope, whereas Elizabeth is going to get energy in a quantized manner by each step she takes. So if she goes up one stair, that's a certain amount of energy she's gotten. She goes up the next stair, that's another energy unit chunk she's gotten. Where again, Tyler just oozing up continuously. Okay, so that's kind of what quantized means. So it's kind of discrete packets of energy. It's not a continuous thing. There are very specific amounts in there. And so these energy levels here will be unique to each atom. Yes, exactly. So quantized means it's incremental energy, whereas something that is continuous energy would just be not quantized. And so we have, our old idea of atomic structure. This is called the Bohr model. Before I talk about this, I have other electron stuff to talk about. Other things can happen. We're going to see that if a copper atom gets hit with a photon, it can enter what is called an excited state. So instead of kicking out the electron, it might just excite the electron instead. So if we give it more energy, remember this little bit here, h nu is energy. We're just giving it more energy. So now it is a more energetic copper atom. It turns out that later, it might spend some time in this electron. I don't know why I drew the electron, but we'll just make it clearer. This light can be emitted again. So remember, with photoelectric effect, you bonk your copper with light, and poof, an electron comes out. Sometimes what's going to happen instead is instead of an electron being ejected, the copper just absorbs the light, holds on to it for a little bit as an excited copper, and then spits the energy back out again. And so it's gone back to what's called the ground state. Ground state is our low energy level. Excited state is the high energy level. If you think about that, I hate doing this, but it usually works pretty well as an explanation. Okay. Let's see. So, Tyler is mad at me now for calling him a snail, and he's got a cattle prod, which is like a little shocky tool, and he's gonna just come up and zap me with it. And what's gonna happen if I get zapped is, oh, I'm too old for this now, but I might jump. And so now, as I am on this rickety table, which I should not have done, I am now higher energy, right? He zapped me, and I got scared and jumped up. And, okay, once the surprise wears off, I'm gonna come down again. And so, ow. Normally I would do this like quite loudly, but I don't want to scare the dogs downstairs. So, what's gonna happen here is that same amount of energy I got by jumping up onto the table is going to be the amount of energy I'm going to release coming down off the table. So, we're going to see that these two energies are the same. So the energy that went in just excited the copper, and what's going to happen is it's going to release it later, and it's going to have the same energy. There are other processes like fluorescence or phosphorescence where it's going to have different energy, but just plain old emission, it will have the same energy. And this one is called absorption, by the way. This one is called emission. Yes, thank you, Tyler. Yeah. I usually like to be loud because then it's like, look at how much energy that was released. But, oh well. Now I'm getting too old and I've got my COVID-15 and all that, and yeah, sad times. Okay, anyways, what that looks like here's our copper atom. Here's an electron in copper. So you've probably seen this kind of modeling of an atom before. These are what are called Bohr models. Where you have the nucleus in the middle and you kind of got these rings around it where the electrons are going. What the excitation looks like is we're going to essentially promote that electron to a higher energy level. So it's going to move into a different orbit. And so that's going to have higher energy, right? We put in energy. Energy is never created or destroyed. So we're going to see that that photon had energy equal to the difference in the orbits. So, in that case, it's whatever this, kind of distance happened to be. It's whatever that distance is in dark blue there. And so, we're going to see that that's going to be a specific energy photon that is able to promote that specific amount of energy to that next orbit. And so we're going to see that all atoms, or all elements rather, have atoms, or have different orbits. Let's see. And what this means is each element has specific energy photons it can absorb. Aborb. Let's try that again. Absorb, or therefore emit. Remember, when it relaxes down, it's going to spit out that energy again, and it's going to be the same amount. And so I have a video of this. Oh my goodness, I'm gonna have to log in real quick because this is gonna be in the textbook that I had. Let's see how to log in. Any questions, by the way, as I log into this? Of course, the password's wrong. Of course, it's still wrong. Notice I type it in one more time and nope, still bad. Okay, let's try with random punctuation. Let's forget it. We go to YouTube then instead. Let's see. This is normally something I would do to show you, but yeah, why not? Okay, here we go.
This is our flame test for our Megalab.
Here is some fire. Oh no. It's fine. I don't want to.
Get into the jar.
Turns out, if we put. Oh my goodness. Notice the fire color here. We're going to give it energy in terms of the fire. And if we put in different elements, they're going to change the color of the fire. So these are all sodium-based salts, it looks like right now. Those all turn the fire that kind of yellow-orange that we're used to seeing fire as. Magnesium. Potassium turns fire purple, though this is kind of hard to see. But you can see it's definitely a different color than the sodium is, right? What's next for us? Calcium. Calcium's boring too. Do copper. Come on. Random person. Manganese, kind of bright yellow. Iron, boring. I want you guys to see copper. Cobalt here. Ah, here's copper. So copper is green. So we get kind of greenish fire coming out of copper-based salts. This is the idea here. This is how fireworks get their different colors as well. Quantum should be more red than this. Barium's green also.
In the second test, I will take the vial with the sample, add an amount of methanol, attempt to dissolve as much of the sample in the methanol as possible, and then remove the methanol salt solution.
But let's
pour
watch.
it
Maybe
onto
it's
a
going
piece
to be
of paper
purple.
towel and ignite it.
It's kind of. Oh. This is just so random. Okay, yeah, lithium's bright red. Anyways, are we boron? Also green. Okay, anyways, that's enough burning things for now. That's the idea. So different elements that they get light or energy. So in this case, they were using heat. Get it? I'm sorry. Did the noise from the fire and YouTube video go through? I hope not. I forgot to turn that off. But I also have my computer muted. Yeah, exactly. So yeah, you could totally bring, I mean, some of these are not environmentally friendly, but like lithium, yeah. Find your friends with bipolar depression, take their lithium pills away and throw them in the fire. It'll turn it red. Please don't do that. But if you were to do that, or maybe they no longer have bipolar depression and they have extra lithium lying around, then you can go ahead and burn it, and it'll be red. So yeah. Okay, so fun. So that's the idea: is that different elements have different energy levels in their atoms, and so they can only absorb and therefore emit different energy levels. Yeah, of course, definitely don't do that if you know someone like that. So yeah, or if you rob a drugstore, how about we do it that way? So if you rob a drugstore and steal their lithium, then you can do it. Lithium is not environmentally toxic, so we'll be okay. However, copper or barium, those would not be good ideas. Those would be pretty bad to introduce into the environment. Okay, so any questions on that? Okay, so in the Bohr model again, remember this was the nucleus in the middle surrounded by rings. The rings represent extra credit for robbing a drugstore or a pharmacy. I'll consider it. You know, Saracosta does have a correspondence program with one of the prisons around. So if you do go to jail, you can still take chemistry. So I guess it could work. So, but joking aside, yeah, please don't do that. Okay, the rings represent what is called the principal quantum number. Fancy, fancy. So the pesticide chemicals are probably more going to be organic things, and organic things don't burn in pretty colors. It's really just metals, specifically transition metals, that burn very nicely. N can go from between 1 and 7. Inclusive. So, and also, that's N is the principal quantum number. Represents the period on the periodic table. So remember that the periodic table has 7 rows, right? Those will be what are represented by this principal quantum number. And so we're going to see that something with 3 rings, oh, they've got potassium in them, then maybe they will. Maybe they'll be purple. So 3 rings means you have this outermost one is N of 3, N of 2, and N of 1. So, that's what these principal quantum numbers mean. And so we're going to see that we have a way. Oh gosh, do I want to? Yeah. So an electron can go from an electron can be excited from a particular principal quantum number, or a shell, as we're going to see, if we give a particular amount of light to it. And that light, remember, is equal to energy, is equal to the energy difference between n equals 1 and n equals 2. To calculate this, hold on, I'm going to have to get the book. Because, let's see. This one, there's specific constants for each atom. So, and these I do not have memorized. Hey, look, I'm kind of close. No, I'm not. I'm not at all close. Let's see if we can't find... Aha! Here is a happy constant. For hydrogen, they have figured out these energy levels. And so the difference in energy level is going to be given to us, the energy levels, rather. These energy levels are super complicated, by the way. They're doing with all sorts of crazy integrals and physics and all that. I have no idea what's going on. I am not into really high-level math like that, applied to things that don't make sense to me. So for hydrogen specifically, the energy is equal to negative a whole bunch of constants times 1 over the principal quantum number. So for number 1, I guess I should explain these. These are all constants. And RH for hydrogen is, I do not have this memorized because I've never really used it. And apparently the book just gives it to us combined anyway. So forget RH. It's another constant. What this equals to is negative 2.18 times 10 to the negative 18 joules. So we're able to see that we can relate this to 2 different energy levels. So this going away, now that I have that number. This is just for hydrogen, by the way. It gets much more complicated for other atoms. Hydrogen only has 1 electron, so it was fairly easy to model it, jumping between different energy levels. When you have different electrons in there, things gets way more complicated. So typically this is just done for hydrogen. Alrighty, and so we can see that the difference in energy level is going to be the energy at one state, final, minus the initial energy. And so, if an electron goes from n equals 1 to n equals 2, given that the energy for state 1 would be negative 2.18 times 10 to the negative 18 joules times 1 over 1 squared, which is negative 2.18, negative, oh my gosh, that number. For the energy for n equals 2, would be that number, let's see, negative 2.18 divided by 4 is, this is not equals, by the way, that should be multiplied by, that's going to be 5.45 times 10 to the negative 19 joules. Did I do that right? Yeah. Cool. Looking at these 2 numbers, the difference in energy we can calculate it. So the difference in energy between those where's Kevin when we need him? He needs to do the math for us. So add that to. There we go. And so doing that, we get 1.65 times 10 to the negative 18 joules. Someone do this? Thank you. Okay, awesome. Is 635? Oh, so did I. I just forgot the 3 existed. So the difference in energy level between those particular levels in hydrogen, we can calculate. And so we can see that this is a light of that many joules, a photon of light equal to that many joules. Let's see if we can see what wavelength that is. Remember that E equals hc over lambda. So 6.66 times 10 to the negative 34 times 3.0 over lambda just put 1.64. Okay. This crazy number here is equal to those crazy numbers divided by lambda. We can do that. So we are going to need to, that tells us that lambda equals HC over E, right? Which is 6.626. Over the energy, 1.64 times 18. Please. Oh, Kevin is here. I didn't see him. Okay, Kevin, go ahead and do the math for me. While he's doing that, let's just calculate the energy for n equals 3. Okay, thank you, Kevin. Notice that's meters. Let's go ahead and look at the energy for the third level. 2.8 by 9. So that's 2.42 times 10 to the negative 19 joules. And so if we look at the energy difference between 3 and 2, we can also see what that's going to be. And so that's going to be, oh, sorry, that's negative. What was the first one? 5.45. The energy for that transition is going to be 3.03 times 10 to the negative 19 joules. If you wanted to see the wavelength of that one, that's going to just be, again, crazy constants. While Kevin is calculating that for us, let's go ahead and look at the energy differences. So this was what we had before for our wavelength, and this was our energy. Looking at the energies, is this energy between 2 and 1 going to be bigger or smaller than this energy? I know we're all over the place with our energies. Which is bigger? So remember, delta E from 2 to 1, I'll just copy the numbers, was 1.64 times 10 to the negative 18 joules. The change of energy from 3 to 2 was 3.03 times 10 to the negative 19 joules. And so we see that this energy is going to be smaller. Okay, so while Kevin is calculating the wavelength for us, we can display this. Etc. We saw that this difference, look, it's very similar to those horrible enthalpy diagrams, weren't they? 1.64 times 10 to the negative 18 joules. from 2 to 3. Thank you, Kevin. Oh, not joules. It's going to be meters, Kevin. It's a wavelength. But this one is actually visible light. Believe it or not, this is 656 nanometers. That falls into our visible light range. We're able to actually see one of these transitions in hydrogen. I guess we're out of time. I'll talk about that tomorrow. But the idea here is that the energy difference is always smaller the higher up you go. So the energy difference is always the biggest from n to 1 to n to 2. And then it gets smaller and smaller and smaller the higher up you go. Okay, and so we're going to see that all of these could be calculated if we really wanted to for hydrogen. The rest gets much more complicated, but the idea here is that these will be energies that hydrogen atoms could absorb and emit. So this particular one is going to be kind of like orange-red light. And so hydrogen, if we give it orange or red light, can absorb that particular energy, and it can release it later. And so we're going to see that if we do a whole bunch of fun stuff with hydrogen, we're going to get fun colors out of it. So there we have it. Exciting. Quantum mechanics, a whole bunch of really small numbers. Lots of constants everywhere. Cool. So we'll continue this tomorrow. We will have more fun with quantum mechanics. We'll talk about, let's see what we're going to talk about. Probably more stuff to do with electrons than light. We're kind of done with light for now, I think. So with that, I bid you adieu. I'll see you tomorrow. And yeah, don't forget your homework is due Saturday for thermochemistry. And I will put up homework for this stuff probably later this week. And yeah, so with that, see you guys tomorrow.